Next, we're going to solve question 9 from the May 2018 paper. This is a question about the Lux formalism for partial differential equations of KdV type. As you can see, it consists of various parts, so we'll start with part A. So we have a function f of x and t, d, which denotes partial derivative with respect to x, and p, q, and r are any differential operators, and we want to show the identities 1 through 4. So let's do that one at a time. Let's begin with the first identity. In part A, we want to show that the commutator of d with f is equal to fx as an operator. So as usual, we act on a function psi, which we'll assume to be sufficiently differentiable. And so this is equal to d times f psi minus f d psi by the definition of a commutator. And as usual, all differential operators act on everything to the right. So the derivative will act on f psi in the first term and only on psi in the second term. For the first term, we can use the Leibniz rule. So either the derivative acts on f, so we get df, which multiplies psi, or it acts on psi, in which case we get f times d psi. And in the second term, we get minus f d psi. That's a negative term in the commutator. And so we see that the commutator of d with f acting on psi is equal to the first derivative of f, which is fx, multiplying psi for all functions psi. And therefore, as operators, the commutator of d with f, where d is the derivative with respect to x and f is a multiplication by a function of x, is equal to fx, so just multiplication by the first derivative of x. That's what we wanted to prove in first identity. Next, we're going to move to the second identity, which involves the commutator of d squared with f. Once again, we act on a function psi, and this is equal to d squared f psi minus f d squared psi. And next, for the first term, d squared times f psi, let's distribute the two derivatives so that they act on f or psi in all possible ways. So one option is that both derivatives act on f. So we get second derivative of f times psi. Another option is that one derivative acts on f and the other derivative acts on psi, and there are two ways of distributing the two derivatives. So we get two derivative of f times derivative of psi, or the two derivative could act on psi only. So we get plus f d squared psi. And then we subtract the negative term in the commutator, minus f d squared psi, which cancels against the last term that we wrote there. So now if I write this, the derivatives acting on f using the subscript, we get fxx, which multiplies psi plus 2fx, which multiplies the derivative acting on psi. And this again is true for all functions psi, and so we deduce that as an operator, the commutator of d squared with f is equal to fxx, which is a multiplicative operator, plus 2fx times operator d, which denotes the first derivative. So that's the second identity. So next we move on to part 3, which involves the third derivative, or the third power of the operator d. The logic is the same. So we have a third derivative acting on f times psi minus f times the third derivative acting on psi. Now there are four options. So the three derivatives could act on f. So we get d3f times psi, or two derivatives could act on f, and one derivative could act on psi. And there are three ways of distributing the derivatives in this way. Or one derivative acts on f, two derivatives act on psi, and there are again three ways. Or all the three derivatives act on psi. And finally, we subtract the negative term in the commutator, which cancels the last term that we wrote. So we get f x x x times psi plus 3fxx times the derivative acting on psi plus 3fx times the second derivative acting on psi. This again is true for all differentiable functions psi, and therefore the commutator of d cubed with f is equal to fxxx plus 3fxxd plus 3fx d squared as an operator. So finally, identity 4 is familiar from linear algebra. It's just the commutator of P with QR. Let's look at that. So we can write this as PQR minus QRP by the definition of commutator. And now we can add and subtract the same term, QPR. So let's do that. So this is PQR minus QPR plus QPR minus QRP. And now we can identify in the first two terms the commutator of P with Q times R, and in the second pair of terms we get identify plus Q the commutator of P with R. Next, in part B, we're going to use some of the identities that we derived in part A. Now we have L and M, two differential operators. L is d squared plus u, and m is minus 4d cubed plus beta d plus gamma, where beta and gamma are functions of x and t, like the field u. And we now need to compute the commutator of L and M, which should be written in a form where the differential operators t to the n are all on the right. So let's do that. Commutator of L and M, L is equal to d squared plus u, and m is equal to minus 4d cubed plus beta d plus gamma. So there are a few terms here. So first we have the commutator of d squared with d cubed. Let me write that down explicitly. But this is clearly equal to 0. So then we have the commutator of d squared with beta d. And we have the commutator of d squared with gamma minus 4 commutator of u d cubed. Then we have the commutator of u with beta d, and the commutator of u with gamma. So this last commutator of u with gamma is 0 because u and gamma are both two functions, so these are multiplicative operators, and u gamma minus gamma u is 0 by the commutativity of the product. Okay, so next let's compute the four non-trivial terms. So first we have a commutator of d squared with beta d. So this is equal to the commutator of d squared with beta, which multiplies d, plus beta, the commutator of d squared with d, using the last property derived in part A. So the second commutator vanishes, and the first commutator is computed in part A. So that's equal to beta xx plus 2 beta xd times d. So this is beta xx d plus 2 beta x d squared. So similarly for d squared commutator with gamma, this is equal to gamma xx plus 2 gamma xd. So next we have the commutator of u with d cubed. That's equal to minus the commutator of d cubed with u. So we get minus uxxx minus 3uxxd minus 3uxd squared. And finally, we have the commutator of u with beta d. So that's equal to the commutator of u with beta times d plus beta, the commutator of u with d. The first commutator of u with beta is 0 because u and beta are just two functions of x and t. And for the second commutator, we use the identity derived earlier. So that's minus beta ux. Now let's put all these commutators together. So now the commutator of L with M is equal to beta x xd plus 2 beta x d squared from the first commutator, and then we have gamma xx plus 2 gamma xd from the second commutator, and then we get minus 4 times this expression here in the third line. So we get plus 4u xxx plus 12uxxd plus 12uxd squared, and finally have minus beta ux. So now let's group together terms which multiplies the same power of d. Let's start with d squared first. So we get this term and that term. So we have 12ux plus 2 beta x, which multiplies d squared. Next, we look at terms which multiply a single power of d, beta xx plus 2 gamma x plus 12 uxx, which multiplies d. And finally, we have terms with no differential operator d. So those are gamma xx plus 4uxxx minus beta ux. Next, in part C, we're asked what property must the commutator of L and M possess in order for L and M to form a Lax pair. So the answer to that question is that the commutator of L and M should be multiplicative. So commutator of L and M must be multiplicative. That is, it should not involve a differential operator. D to the n. So it should just multiply by a function. And next, we are asked to use this property to find beta and gamma in terms of two unknown functions of t only. So now let's impose that the commutator of L and M computed above is multiplicative. So that means that the first bracket here, which multiplies d squared, must vanish. And the same for the second bracket, which multiplies d. Okay, so let's look at this term by term. So let's first set the coefficient of d squared to 0. So that's 12ux plus 2 beta x is 0. And so by integration, we see that beta is equal to minus 6u plus an integration constant f. which is constant with respect to x, the variable that is differentiated, but therefore could be a function of t. So that's an integration constant, but only constant with respect to x. So it's an arbitrary function of t. Okay, so next we move on to the terms of order d. So we want to set 0 beta xx plus 2 gamma x plus 12 uxx. And now we can use the expression that relates beta and u above. So we take 2x derivative. So beta xx will be equal to minus 6 uxx. I get still plus 2 gamma x plus 12 uxx, which is equal to 2 gamma x plus 6 uxx. So again, we can integrate with respect to x, and we get that gamma is equal to minus 3ux plus another integration constant with respect to x, which will be a function of t. Let me call that g of t. So this answers part C, where we determine beta and gamma in terms of two unknown functions of t only, which we call f of t and g of t. So next in part T, we want to show that the Lux equation, time derivative of L plus commutator of L with M is equal to 0, implies a KdV equation for a particular choice of one of the unknown functions of T that just appeared in part C. So let me remind you that in part C, we obtained that the commutator of L and M, after we impose a condition that this was a multiplicative operator, is equal to gamma xx plus 4uxxx minus beta ux. And beta and gamma were determined in terms of u as follows. Beta was minus 6u plus f, and gamma was minus 3ux plus g, where f and g were the two unknown functions of t. So now let's plug these expressions for gamma and beta inside the commutator. So first we have gamma xx, that's minus 3uxxx. Then when we differentiate g of t with respect to x, we get 0. So next term is plus 4uxxx. And the final term is minus beta times ux. So minus beta is equal to 6u minus f of t, and that multiplies ux. So we get uxxx plus 6ux minus f of t times ux. So therefore, the Lux equation, which tells us that the time derivative of L plus the commutator of L with M is 0, can be written as follows. I remind you, L was equal to d squared plus u, which is a function of x and t. So the time derivative of L is simply the time derivative of u. And then from the commutator, we have uxxx plus 6ux minus f of t times ux. So this is the KdV equation only if f of t is 0. And for any choice of g. So in particular, we could also take G equal to 0. This was part D. Finally, in part E, we are asked to indicate how one can generalize this method to obtain higher order nonlinear partial differential equations for U, which are solvable by the inverse scattering method. So here, I remind you, the logic was that whenever a partial differential equation could be rewritten as a Lax equation for a Lax pair of L equal to D squared plus U and M given by some differential operator to be found in such a way that the commutator of L and M was multiplicative, then we could indeed use the power of the Lax formalism to use this inverse scattering method. So to answer part E, I would write, we can try higher order differential operators, Mn. Actually, they can be taken without loss of generality to be anti-Hermitian. So let me write that. Differential operators Mn so for example, for M5, we could take this to be d to the 5th power plus something like alpha d cubed plus d cubed alpha plus beta d plus d beta plus gamma. If you don't remember that, they can be taken to be anti-Hermitian. That would be fine. And then requiring that the commutator of Ln M5 is multiplicative. Determines the unknown functions alpha, beta, and gamma, possibly up to integration constants, which are actually functions of t. Then the Lax equation Lt plus commutator of L with Mn equal to 0, with L again given by d squared plus U, is equivalent to a generalized KdV n equation, where n denotes the degree of Mn, which is of a form that ut is equal to a function of u and its x derivatives up to the nth derivative of u. And in fact, the nth derivative of u appears linearly. So iterating this exercise for all values of n, and here n has to be odd if you want Mn to be anti-Hermitian, produces a hierarchy of partial differential equations which are solvable by the inverse scattering method. and are known as the KDV hierarchy. So that would have been my answer to part E, but I guess even something with a little less detail, but with the main ideas would also do. That concludes the solution to question 9 from May 2018.